All right.
Yes.
So that gives you an encouragement point. Where is it?
Yes. Thank you, teacher.
All right. Huyền Trang. All right. And now, how about questions B? Anyone? Okay, so I see this hand first. P. Phạm Thu Thảo.
Yes.
Yes. Okay, so can you help me to solve problem B? Oh, wait a minute. Okay, so questions B.
So the correlation coefficient equal the covariance between I and RB
Okay,
divided.
so questions B. Just wait a minute. Questions B. You are asked to calculate the correlation coefficient between the returns of the two investments. All right. So the lower three round form a matrix, a covariant matrix between the returns. Then you can see that you can look at one value here and look at the column or the round name. You can see that it will be it is the covariance between which two variables. For example, 0.81 here is the covariance between RA and RA, which means that 0.81 is the variance of RA. All right. And 0.0648 is the covariance between RA and RB. All right. So here we have the covariant matrix between the return. All right. Now you have to calculate the correlation coefficient. You have to find the relevant covariance or standard deviation of the return and replace into the formula. All right. Now, Thảo, continue.
Is equal the covariance between RA and RB.
Okay, the covariant. Sorry, wait a minute. The correlation coefficient. Let's call it small r AB, for example. Okay, equal the ratio between the covariance of RA and RB. All right, divided by
The standard deviation of A multiplied by the standard deviation of B.
okay, so it will be equal to the okay, divided by the products between the standard deviation of RA multiplied by the standard deviation of RB. Okay, and what is the covariance between RA and RB?
It's 0.0648.
All right. And what is the standard deviation?
It's equal to square root of 0.81.
Square root of 0.81
multiplied by 0.0144.
0.0144. Okay, and what is the value?
It's equal 0.6.
0.6. Okay, so the correlation coefficient between RA and RB here is 0.6. All right. Thank you. Do you get the same result?
Yes. Yes.
Okay, good. So the standard deviations of RA is 0.9. Oh, it's really high. Okay. All right. So thank you, Thảo. Let me Okay, give you an encouragement point. Phạm Thu Thảo đúng không ạ?
Yes, thank you, teacher.
Okay, and the last one, question C. Okay, I see Bùi Ngọc Linh. Bạn Đức Trung. I'll call you later, Trung. Okay, so Bùi Ngọc Linh first. Our questions here is to determine the standard error of the return on the portfolio. Okay.
To calculate the standard error, I think first we need to calculate the standard deviation.
The standard deviation. Actually,
Of
now we want to calculate the standard error of the return on the portfolio. In order to calculate the standard error, you have to calculate the variance of the return on the portfolio first, then take the square root of that
square root.
value. Yeah. Now, first,
Uh,
let's have me please help me to calculate the variance of the return on the portfolio. And now we repeat the formula for the return on the portfolio RP is equal to 0.75 times RA and plus 0.25 times RB. Okay. Now, what is the variance of RP?
the variance of RP is 0.75. Cô em không nhớ mũ 2 tiếng Anh là gì ạ?
Square. All right.
Square multiplied by 0.9
Okay.
multiply
So, please write down the formula first. Okay. Then we have variance
of
of RA.
RA
Okay.
plus 0.25
Square.
square multiplied by variance of return rate of B
RB. Okay. And
plus 2
times, yeah,
one
75. Okay.
and 0.25
Yeah. And
and the covariance of RA RB.
yeah, and RB, the covariance between RA and RB. And now look at the covariance matrix and replace the number here. We have 0.75 square multiplied by
0.9 square.
okay, so 0.18 as
Yes.
shown in the matrix. Okay, plus
0.25 square
okay,
plus 0.0144
144. All right, and then
plus
plus 2
2
0.75 multiplied by 0.25. Okay, and multiply by the covariance
0.0648.
for 8. All right, and then what is the result?
We have mm, 0.48.
For 8. All right, and what is the standard error? Standard error of RP
The standard error will be
will be
0.
square
The
root
square root of
yeah,
0.48 divided by
It the standard error is what that we use for the sample standard deviation. Okay, standard deviation is the words that we use for the population, and for the sample we use standard error. Okay, and here the standard error is the square root of the sample variance, because here we have the sample data, the sample statistic. Usually in reality we do not have the exact information of the parameters of the populations. We usually have the sample statistic. Okay, then here please call it the standard error and the sample variance of the return of the portfolio. Okay, so the standard error here is just the square root of the variance of the return on the portfolio. All right, and what is the value?
It will be 0.69.
Okay, 0.69. All right, so the answer for questions B is 0.69. The 0.69 is the standard error of the return on the portfolio. Okay, do you get the same result?
Yes.
Okay, thank you. All right. Uh, Ngọc Linh just answer the question C, right?
Yes.
Okay, thank you. Let's give you an encouragement point. Where's you? Ngọc Linh over here. All right. Thank you for your answers. Do you have any questions here? You have the formula and you just have to plug in the number into the formula to get the result. All right. Do you have any questions here? No? Okay. All right. So let's come to our discussions today about the some important probability distribution and statistical inference. All right. Firstly, let's talk about some important probability distribution. The first one that we want to mention here is the normal distribution. So normal distribution, do you remember that? It is the most common type of distribution assumed in finance and economics. All right. For example, most of the distribution of stock market return, okay, uh, and have normal distribution. All right. So if we have an x variables and x follow normal distribution, we will write it like this: x follow normal distribution. Normal distribution has two parameters, that is the mean mu here and the variance sigma square. Okay. All right. And normal distribution is denoted as a big N here. All right. It has probability function like this. Actually, I have to correct this. We have sigma should be outside the square root. All right. But you don't have to remember. You don't have to remember the formula. Okay. We just remember that every distribution has a probability functions x. Okay. And this the shape of the normal distribution. All right. You can look at this. It is symmetric, right? Symmetric distribution. It has the mean of mu and the standard deviation of sigma. Okay, so we have 68% of the observed value, for example, x follow normal distribution. Here are the observed value of x. Okay, and 68% of the observed value of x will fall into the range from mu minus sigma to mu plus sigma, which is a plus or minus one deviation from the mean. All right, 95% of the observed value of x will be in the range that is plus or minus two deviations from the mean. All right, and most of the observed value of x, almost 100%, is 99.7% of the observed value of x lie into the range from minus or plus 3 times the standard deviation from the mean. Okay, so that is the that is a constant probabilities, okay, of the normal distribution. All right, normal distribution has a bell-shaped curve, or you can say that inverted U shape. All right, okay, and that is the most common distribution in statistics and probability. You don't have to remember the distribution function of it. Okay, just remember the shape. Is it symmetric or not? Okay, and the ratio of the percentage of the observed value between each ring. Okay, in each ring. All right. Do you have any questions about the normal distribution? You have learned it in statistics and probability. We just review it here. All right. All right. So next, standardized normal distribution is a special type of the normal distribution. It's a normal distribution, but we know, okay, we know the expected value. It has an expected value of 0 and the standard deviation or the variance of 1. Okay, for a normal distribution, the expected value can be any value. Okay, and the variance also can be also anything. All right, but for a standardized normal distribution, the mean value has been 0 and the variance must be 1, and we denote the standard normal distribution with a z like this. Okay, we say that x follow standardized normal distribution. All right, so here's the function, the probability function for a standardized normal distribution. And this is the shape of the distribution like this. Okay, we have 0 at the center and the standard error, also standard deviation of 1. Okay, 80%, 86, sorry, 68% of the observed value of x will be between -1 and 1. 95% of the observed value of x will fall into the range from -2 to 2, and 99% of the observed value of x will be in the range from -3 to 3. Okay, so if we have x value, okay, if we have x variables that follow a normal distribution with the expected value of mu and the variance of sigma square, then how can we standardize this normal distribution? How can we turn the normal distribution of x into a standardized normal distribution of another variables? How can we do that? Remember that. Remember, in this case, we know the exact value of sigma square. Okay, we get the exact value of the parameter sigma square. Then how can we standardize the normal distribution of x? Okay, we can say that we turn the normal distribution of x into the standardized normal distribution of another variable. Do you remember the formula that we can do that?
I think I do remember a little bit.
What is it?
Uh, Z equals x minus me divided by standard deviation.
Okay, so we take the observed value of x minus the population mean mu, then divided by the standard deviation sigma. Okay, let's call this z variable. Z variables, and this z will follow a standardized normal distribution. Okay, so if we use this formula to calculate z, then we have a lot of z, okay, because we have a lot of observed value of x. So each observed value of x will have a corresponding value of a corresponding value of z, okay, and we have a lot of z here, and z variables will follow a standardized normal distribution. All right. But remember that in this case, we know the exact value of sigma square, the variance of the population. All right. Okay. The next distribution that we would want to mention is the chi-square distribution. Chi-square distribution. If we have z1, z2, so on to zk, independent standardized normal variables, then the sum of the square z, okay, we have the sum of the square z's will follow a chi-square distribution with k degree of freedoms. Okay, so normal distribution is a symmetric distribution, and standardized normal distribution is also a symmetric one, but it only has they only have two parameters, which are the mean and the variance. But for chi-square distribution, we have another thing that we call the degree of freedoms. Okay, and then later you will see the importance of the degree of freedoms for a chi-square distribution. All right. So the sum of all square z will follow a chi-square distribution. Okay, so this is the shape of chi-square distribution with different degree of freedoms. Now look at the figure. All right, you can see that the share chi-square distribution is not a symmetric distribution. Okay, it is often uh, like is not symmetric. And what else? We can see that for different degree of freedoms, the chi-square distribution has a different shape. Okay, this is the case when the degree of freedom is 2. Okay, and when the degree of freedom is 5, and this is the case when the degree of freedom is 10. Okay, so the degree of freedom is the number of z here. Okay, is the number of z in this sum. All right, and you can see that for different degrees of freedom, the chi-square distribution will takes on a different shape. Okay, and what happened when it has different or different degree of freedoms? Now, as we care about the probabilities that our variables has the value fall into a range for continuous random variables. Okay, where's my pointer? Okay, let me clear this. So for example, we let's call, okay, we have x variable and x follow a chi-square distribution. Sorry, x follow a chi-square distribution here. Okay, so we want to know what is the probability that x has the observed value fall into a range that is a to b, for example. And what will be the value for each distribution here? Okay, so for the case when the chi-square distribution has a degree freedom of 2, the probability that x has the value fall into the range from A to B will be this area. Okay, and if the chi-square distribution has the degree of freedom of what 5, okay, this will be the probability, the areas, this area will be the probability that x has the value fall into the range from A to B. And if the distribution that we consider here has the degree of freedom of 10, for example, then this area will be the probability, this area will be the probability that x has the observed value fall into this range. Okay, for so for different degree of freedoms, the probabilities that our variables has the observed value fall into the range is different. So remember, when you talk about a chi-square distribution, please specify what is the degree of freedom of that distribution. All right, because it will determine the probability that our variables has the value fall into a range. Okay, that is chi-square distribution. Okay, and the skewness depends on the degree of freedoms. You can see that. And the mean and variance of a chi-square distribution are k and 2k's respectively. Okay, do you have any questions here? Or if you don't understand anything, you can turn on your mic and ask me to explain again. Okay, all right. Next.
So,
Okay.
so why are the mean and variance are k and 2k respectively? I don't really understand why that's the case.
Yeah, excuse me. Can you repeat
Uh,
that?
I don't understand why the mean and variance are k and 2k respectively.
Oh, okay. All right. So we use some mathematical techniques here. Okay. We use some mathematic techniques here, and it will help you to prove that the mean and the variance of Q here, okay, are K and 2 times K respectively. Okay. Just use some mathematical techniques that you learn from high school. All right. But you don't have to prove that here. Okay, we all know it from the statistic and probability, and we just remember it that. All right. Okay.
Okay, I understand.
All right. Now, next, student T distribution here. We will talk about T distribution a lot in our course. Okay, so Z1, if we have Z1, it has a standardized normal distribution, and Z2 follow chi-square distribution with k degree of freedom. Then a T that is calculated by the ratio between z1 and the square root of the ratio z2 divided by k. This t will follow a student t distribution with k degree of freedom. Okay, so like the chi-square distribution, student t distribution also has a degree of freedoms. All right. Now, do you remember the shape of t distribution? Is it symmetric or asymmetric?
It's symmetric.
Symmetric, right? The distribution of t is symmetric and it has a expected value of 0. Okay, this is the shape of t distribution, and you can see that like chi-square distribution for different degree of freedom, then the t distribution will have different shape. Okay, this is the case when the degree of freedoms is 5. This is the case when the degree of freedoms is 20, and this is the case when the degree of freedoms is 120. Okay, so um, which distribution do you think look which distribution do you think the t distribution look like the most? Which distribution?
Standardized normal distribution.
Yeah, thank you. The standardized normal distribution. Uh, the t distribution looks like the standardized normal distribution the most. Okay, when the degree of freedom increase, it will approach the standardized normal distribution. Okay, the t distribution has the mean and variance of 0 and the variance of k divided by k minus 2. Okay, this also um, derived from some mathematical techniques. All right, and as you see, the variance of the t distribution is k divided by k minus 2 when the degree of freedom increase. Okay, when the degree of freedom increase to infinity, then this variance will approach 1. Okay, and which means that when the degree of freedoms increase, the t distribution will become more um, uh, close to the standardized normal distribution. All right. If we have x value follow this normal distribution with the expected value of mu and the standard norm, then the variance of sigma square. But in this case, we do not know the exact value of sigma square. Okay, we have to use the sample variance to estimate the population variance. All right, then a t value that calculated by the formula x minus the population mean mu and divided by the standard error s. Okay, this will follow a t distribution with n minus 1 degree of freedom, where n is the sample size. All right, in this case, remember that in previous case, when you know the exact value of sigma square, then x minus mu divided by sigma will follow a standardized normal distribution. But in this case, we do not know the exact value of the variance. Okay, we do not know the exact value of square sigma here. Okay, and we have to estimate sigma square by the sample variance, that is square s. Okay, that is the sample variance. Then x minus mu divided by s, the standard error, will be equal. Will follow a follow a t distribution with n minus 1 degree of freedoms, where n is the sample size that we of the sample that we use to calculate this S. Okay? All right. So there's two different cases when we know the value of sigma square and when we don't know the value of sigma square and have to estimate it by the sample variance. All right. Okay. Next, the final one, F distribution. So Fisher distributions, when we have Z1 and Z2 are independently distributed chi-square variables with K1 and K2 degree of freedom, okay, then the ratio between Z1 divided by K1 and Z2 divided by K2, this ratio will follow an F distribution with K1 and K2 degree of freedoms. So chi-square distribution and T distribution has 1 degree of freedoms, all right? But for F distribution, the Fisher distribution, we have 2 degrees of freedom. That is the numerator degree of freedoms and the denominator degree of freedoms. Okay, 2 degrees of freedom, K1 and K2. And like the chi-square distribution and the student T distribution, the degrees of freedoms of the Fisher distribution also determine the shape of the F distribution. Okay, and here, for example, we have this the shape of the F distribution with if with K1 equal to 2 and K2 is also equal to 2. Okay, this is another F distribution with different degrees of freedom, 10 and 2. And this one, the F distribution has the degrees of freedoms of 50 and 50. Okay, so for different degrees of freedom, then the Fisher distribution also has different shape. All right. So when you talk about an F distribution, remember to determine or to specify the degree of freedoms of that distribution, right? The F distribution is also not symmetric, all right? And the value of F is always equal or greater than 0. Is non-negative number, okay? Just like the chi-square distribution, if x follow a chi-square distribution, then the value of x will be a non-negative, okay, non-negative number. And also the same happen for Fisher distribution. If x follow a Fisher distribution, then the value of x will be a non-negative number. Okay. Okay, this one we can pass it. Okay. So that as the most important distribution in statistic and probability that we will mention in this course. Okay. Later in the course, we will see each of these probability distribution, okay, and we will discuss about them more. All right. The next part will be statistical inference. So what is statistical inference? Do you remember statistical inference? Statistical inference, what is it? So remember that when we do a research about a population, okay, we usually want to know about the population parameters, okay? The population parameter are the characteristic of the whole population of interest. We can do that. We can find out the characteristic of the population by collecting the data of the whole population. For example, there are two way that we can there are two ways that we can do to know about the population parameters. The first one is to collect the data of the whole population of interest. All right. For example, when we want to know about the income of all household in Hanoi, when we do research, when we investigate the income of all households in Hanoi, we want to know what is the mean income of all household in Hanoi, and how spread out the observed income of household are around the mean. Okay, for example, those parameter, mean and the variance of the income of our household in Hanoi. We can get the information about the population mean and variance by collect the data of income of our household in Hanoi. All right, and calculate the exact value of the population and the mean. But this but this way is mostly what is it? Unrealistic. Okay, because it will be very time consuming or costly to collect the data of all household in Hanoi. Or some household are not willing to provide you with the information that you need. All right, so it is impossible for it to collect the data of all the population of interest. So the second way that we can do to collect to get the information about the population parameters is to collect a random sample from the population. Okay, we want to collect a random sample from the population, and then from that sample we calculate the sample statistic, and later we use the sample statistic to make some inference about the population parameters. Okay, in this way we will only get an approximations of the value of the population parameters. All right, and that is called the process of statistical inference. So statistical inference includes two main tasks, that is estimation and hypothesis testing. Okay, you also you all know that from statistic and probability, right? Okay, so to demonstrate those that we will take an example here. Okay, so for example, we care about the weight of the tea bags manufactured by a company that's called, let's call that company the company X, for example. Okay, and we want to know the average weight of the tea bags manufactured by that company. Okay, or the population mean. Now we cannot collect the data of all of the weight of all tea bags manufactured by that company. Third, we choose the second way. Okay, we take a random sample. We take a random sample of 36 tea bags manufactured by that company, and that sample provide a sample mean. Okay, the sample mean is 19.7 grams. Okay, so from that from the sample statistic, what can we say about the population mean, which is the average weight of all the tea bags manufactured by the company? What can we say about it? All right, there's two tasks that we want to mention here: the estimation and the hypothesis testing. For estimation, we have point estimation. We can use the sample statistic to assign uh, the population parameters. Okay, we say that okay, the average weight of all tea bags manufactured by this company can be 19.7 grams, like the sample average, the sample mean. Okay, all right, that is the point estimation. However, sometimes, actually, in fact, the population mean or the average weight of all tea bags manufactured by this company can be 19.7 gram, but it can also be different from a little different from 19.7 grams. Okay, it can be 20 grams, it can be 90.5 gram, for example. Okay, so for to make us more safe, we want to use the interval estimation. From the point estimation, we usually broaden the range. Okay, we create a range around the point estimation. All right, and that range is wide enough so that we believe the actual value of the population mean will be within that range. Okay, so we usually say the interval estimation will give us the answer, um, in which range or in which interval the actual value of the population mean will fall into. All right, that is interval estimation. And another task of statistical inference is hypothesis testing. Okay, a hypothesis is usually our doubt or our belief about the characteristic of the population. Okay, for example, in this case is the population mean. So the supplier or the company state that the tea bags has a weight, an average weight of 20 gram. But when we take a random sample and we calculate the sample mean is 19.7 grams like this, we can believe that, okay, based on the sample statistic, all right, we can believe that the actual average weight of all tea bags manufactured by this company can be less than 20 gram. Okay, so is that belief justified, or can we find the evidence? Can we find the evidence to support the belief that the average weight of our tea bag manufactured by this company is less than 20 gram? Okay, so if you can find the evidence, okay, the process that we try to find the evidence to support that hypothesis is called hypothesis testing. All right. Okay, so in hypothesis testing, we will have to um, establish the null hypothesis, the alternative hypothesis. We have to calculate the test statistic and then determine the rejection zone and then draw a conclusion. Okay, that all the things that we do in hypothesis testing. Okay, we just review it here. Now, for the pi estimation, you just have to take the value of the sample statistic to assign it to the value of the population parameters. Is it is a very easy task that we will not review here. Okay, we will begin with the interval estimation. But before that, we want to talk more about the statistical inference. So, like we say, we have two tasks in statistical inference, and the main purpose of those tasks involve in searching for an estimators that allow us to gain the information or to gain the insight into the value of the unknown parameters. Okay, so because we do not have the data, we do not have the full data of the whole population of interest, we cannot calculate the exact value of the population parameters. We cannot do that. Okay, so we just take a random sample and calculate the sample statistic, okay? And we use the sample statistic to get an approximation of the population parameter. That's why we call the unknown population parameters. We do not know the exact value of it, okay? And we have to use sample statistic, that is the realization of the estimators, okay, to get the information to gain insight into the value of the parameters. All right, so what is an estimator? So an estimator is usually a formula, okay, is a rule or a formula that tells us how to go about estimating a population parameters. For example, the sample mean, the formula for sample mean is the average. You can take the observed value of x1 plus the observed value of x2 and plus so on to the observed value of xn, okay, and divided by n. That is the formula to calculate the sample mean, and we call it an estimator. Okay, an estimator of the population parameter, of the population mean. Okay, so estimator is a formula. Okay, um, and for different, okay, because it's a formula for different sample, okay, you will have different value or realization of the estimators. Okay, the realizations of an estimator, the realization of a formula is called an estimate. Okay, so estimators is a formula and estimate is a value. Okay, is a number. Okay, is the realization of the formula. All right, so for one estimator you may have a lot of estimate corresponding to different sample taken from the population. All right, so estimator can be considered, can be seen as a variables. Okay, it has different value in for different samples. Okay, and those value we call it the estimate. All right, so estimator is a formula and it is a random variables, and estimate is a value. Okay, and is what is it? It determined, is determined for each sample. Okay, all right. Do you have any questions here? Is not clear enough? Um, do you want to me? Do you want me to re-explain the difference between estimator and estimate? Okay, okay. Uh, all right. So you all got it. All right. Before we move to the interval estimations, let's discuss the central limit theorems that will also be used, that we will also mention again in the next chapter. Okay, the central limit theorem from statistic and probability. So this theory state that the average calculated from independent identically distributed random variable x, if we have x1, x2, x3 and so on to xn, are independently identically distributed, okay, with the expected value of mu and the standard deviation of sigma. Then when the sample size is sufficiently large, we will have the sample mean. Okay, the mean, the estimator. This is the estimator. Okay, the sample mean will follow a normal distribution with the expected value of mu and the standard deviation of sigma squared divided by n. Okay, this is the central limit theorems. Okay, when we have n sufficiently large, we do not care about the underlying distribution of x. Okay, regardless of the underlying distribution of x, the mean, okay, the sample mean here will always follow a normal distribution. Okay, that is the central limit theorems. And so when the estimators follow a normal distribution like this, we can use the distribution of these estimators to construct the interval, the confidence interval for our unknown parameters, the population mean. Okay. All right. Now we will take advantage of the distribution of the sample mean, okay, to construct the confidence interval for the population mean, that is the MUI. Okay, in this case, remember that we will divide it in two cases. The case when we know the value of sigma square and the case when we do not know the value of sigma square. All right. Now, the first one, when we know the value of sigma square, okay, and we do not know about the value of MUI, we want to construct the confidence interval for MUI. All right, then in this case, we have x follow a normal distribution with the expected value of MUI and the the variance of sigma square. And from the central limit theorems, we have the sample mean of x, okay, will follow a normal distribution with the expected value of MUI and the variance of sigma square divided by n. All right. Now we will take advantage of this one. Okay. So in the case when we know the value of sigma square, we have sigma square, we have the exact value of sigma square, then the sample mean of x bar minus divided by sigma, this one follow a z distribution with zero mean and variance of 1. All right, so the normal distribution of x bar is equivalent to the standardized normal distribution of z. So we will take advantage of that to construct the confidence interval for MUI like this. Okay, so we will begin with the confidence interval for z first. Okay, we have here is the distribution of z, a symmetric one with zero mean. All right, so if here we have a z star, okay, z star, so that for the probability that we can have that z has a value that is larger than z star, okay, this probability is equal to alpha divided by 2, then we call z star z alpha divided by 2. Okay, and because this distribution is symmetric, then okay, here we will have a value that called minus z alpha divided by 2. And because the distribution is symmetric, then the probability that we can have that z have a value smaller than minus z alpha divided by 2, this probability is also equal to alpha divided by 2. Okay, so because Okay, this area has the value of alpha divided by 2, then the middle will be 1 minus alpha, which means that the probability that that z has a value fall into the range from minus z alpha divided by 2 and less than z alpha divided by 2, this probability is equal to 1 minus alpha. Okay, so the interval from minus z alpha divided by 2 to z alpha divided by 2, this is called the confidence interval. Okay, the confidence interval of the observed value of z, okay, with sorry, at alpha level of significance. Okay, and similarly, okay, we will construct the confidence interval from we, okay, because the distribution of x bar and the distribution of z is equivalent, then from the distribution of z we will have, okay, so because z here, you can see that z, the observed z, equal x bar minus mu divided by sigma, then, all right, we can replace this into the probability here. We have the probability, all right, that x bar minus mu divided by sigma, okay, greater than z minus z alpha divided by 2 and less than z alpha divided by 2. Okay, this probability is equal 1 minus alpha. All right, so we just do some mathematical transformation here. All right, we sorry, this one divided by, okay, sorry, this one must z equal x bar minus mu and divided by sigma and divided by the square root of n. Okay, because the variance of x bar is sigma squared divided by n. All right, so just do some mathematical transformation here. We have p, the probability that minus z alpha divided by 2 multiplied by sigma divided by square root of n smaller or equal to x bar minus mu, okay, and smaller and less than z alpha divided by 2 multiplied by sigma divided by square root of n. This probability equal to 1, not this, 1 minus alpha. Okay, we want to construct the confidence interval from mu. That's why here we want to do the mathematical transformation so that in the middle we only have mu. Okay, so we will not minus, okay, the probability, okay, probability that minus x bar, okay, minus z alpha divided by 2 multiplied by sigma divided by square root of n smaller or less than mu, okay, smaller or less than minus x bar plus z alpha divided by 2 multiplied by sigma and divided by square root of n. This probability is equal to 1 minus alpha. All right, And finally, sorry, we have a minus here. Okay. And finally, we want to multiply all this by -1 to get a mui, okay, a positive mui in the middle. We have the probability that plus z alpha divided by 2 multiplied by sigma and divided by square root of n. Now we have to switch the sign, right? Greater or equal to me, greater or equal to x bar minus z alpha divided by 2 multiplied by sigma and divided by square root of n. This probability is also equal to 1 minus alpha. And from the definition of confidence interval, we can see that the range from x bar, okay, minus z alpha divided by 2 multiplied by sigma divided by square root of n to x bar plus z alpha divided by 2, okay, and multiply by sigma divided by the square root of n. This range will be the confidence interval, okay. But alpha level of significance. Okay, that is what you learned from the statistic and probability, right? Okay. Then we have the formula for the confidence interval of mu. Okay. And for example, in this sample, we have the sample mean x bar is 19.7, and given that we know that the variance of the standard deviation of the population is 1 gram, then we can calculate the 95 confidence interval, or the confidence interval with the level of significance of 5%. Okay, can you help me to calculate the confidence interval for mu in this case? What is it? What is the z 0.025? What is the value of that critical value? Z 0.025. How can we, okay,
1.80 analysis.
1.96. Okay, 1.96. All right. Okay, so for the critical value, z alpha or z alpha divided by 2, you just look at the statistic table, okay? You look at the distribution table of z and then try to find out the critical value, okay? For the case when we have alpha is 0.5, also 0.05, then we will have z alpha divided by 2, get the values of 1.96, is it? Yeah, 1.96. We have x bar here is 19.7 minus 1. Z alpha divided by 2, 1.96. Okay, multiplied by sigma, that is 1, and divided by square root of n, which is square root of, say, 36. All right, and 19.7 plus 1.96 multiply by 1 divided by square root of 36. And what is the interval? Can you calculate and get the
19.377.
19.373.
uh, can you speak louder?
19.373.
73
Yeah.
to
To 0 to 20
oh,
20.026.
okay, thank you so much. All right, so this is the 95 confident interval for we. All right, okay, so what happened when the sample size increased? What happened when the sample size increased? What happened to this confident interval?
The interval becomes smaller.
Yeah, right. The interval will become smaller, right? We say that it's will shrink, right? Okay, and for our estimation, is this better for our estimation?
Yes.
Yes, of course. Okay, we will have closer. Okay, we will get closer to the exact value of the unknown parameters that we care about. Okay, okay. So that is the importance of sample size. When sample size increase, okay, our estimation will become more reliable. Okay. Okay, we will get more information, we will get closer to the unknown parameters. All right. Okay, next. So what happened? What if we do not know the value of sigma square? Okay, what if we do not know the value of sigma square and we have to estimate it? Okay, we do not know the value of sigma square and we have to use the sample. Okay, the sample mean, so the sample variance, we have to use the sample variance square s to estimate the population variance sigma square. Okay, we have to use the sample variance to estimate the population parameters. Then the confidence interval for we. Do you remember it? In this case, the critical value will not be z anymore. Okay, it will be. Do you remember the confidence interval for we? In the case that, yeah, yeah, we will use t, critical value of t, not the critical value of z anymore. All right, and the interval, the confidence interval for the confidence interval for we, in this case, okay, it will look like this. We will use the critical value of t, not the critical value of z anymore. Because remember that when we do not know the value of mu, then x bar minus mu divided by s, this one will follow a t distribution with n minus 1 degree of freedoms. All right. So in this case, in this example, okay, if sigma is unknown, but from the sample of 36 T-bags, we calculate the sample variance, and then we take the then we get the value of the sample variance is 1 gram. Okay, and that's why the standard error is also 1 gram. Then what will be the confidence interval for the sample mean with the level of significance of 5%. What will be the confidence interval for Mui at the level of significance of 5%? Now just replace the number into, plug in the number into the formula. Anyone? Can you look for the value of t? Look up the value of t.
2.0301.
2. Okay. Do you know how to look up the value of t in Excel?
We use the T table.
You can use the t table. Okay. For example, let me try to find this. Oh, we have it in the textbook. Yes. Okay, we have it in the textbook. Where is it? Appendix. I think I have the bookmark here. Oops. Here, statistical table. Yeah, we have the statistical table here, and here's the t table. Okay, you can look up the value of t in this case. We have, what is the degree of freedom? What is the degree of freedom of the t distribution in this case?
35.
N minus 1.
We have n minus 1, and we have n equal to 36. Then the degree of freedom is 35. Okay, but we do not have 35 here. Okay, but we will take the meter. Okay, we will take the average of between 30 and 40. Now, look at this table. Find the level of significance. We have a two set. We are constructing a symmetric confidence interval or two-tail confidence interval. Then we have to use the lower round. Okay, 0.05 here, and down. Okay, what is the value of it? Can you? Okay, so we will take the average of 2.04 and 2.02, right? We will take the average of it, and we will get 2.03, right? That is the critical value of t in this case. But we can also use, you can also use Excel to get the exact value of the critical t. Okay, we have the function in Excel to identify, to determine the value of t, of critical t. You can use the function if you are conducting a two-tail test, or you are constructing a two-tail confidence interval, then use the function t dot inv dot 2t. Okay, this one stands for two-tail. Okay, and in the parent test, you provided two parameters. The first one is the level of significance, 0.05, and the second one is the degree of freedom. In this case, it is 35. Okay, and then enter. Then we get the value of critical t. Okay. All right. 2.03. Okay. The same as you do it, as you look the same value when you use the t table. All right. And the confidence interval for me will be 90.7 minus 2.03 multiplied by 1 divided by the square root of 36, okay, to 19.7 plus 2.03 multiplied by 1 divided by square root of 36. And what is it?
18.66
to
19.33. 19.
19, sorry. 19.33.
33.
Okay. All right. Okay, so here will be the confidence interval of we, okay, when we don't know the exact value of sigma square, okay. Remember which case, okay, which case we are considering, all right, when we know the value of sigma square or when we don't know the value of sigma square. Most of the cases we do not know the exact value of sigma square and we have to use the t distribution. All right. Okay. Next. The last one, hypothesis testing. So the customer believes that from the sample statistic, okay, based on the sample statistic, customer believe that the average weight of all tea bags manufactured by that company is less than 20 grams. So is the claim justified, or do we have enough evidence to support the belief of the customer? Okay, so it will be a test. Okay, it will be a test to have to determine this. In order to conduct a test, the first step we have to establish, we have to state the hypothesis, the non-hypothesis, and the alternative hypothesis. That is the first step. So what is the hypothesis here? Okay, what is HO? But actually, you should determine the alternative hypothesis first. In hypothesis testing, what we believe, what we want to prove, we usually put it in the alternative hypothesis because the purpose of hypothesis testing is to reject the non-hypothesis. Okay, we have HO, the non-hypothesis, and H1 or HA, the alternative hypothesis. Like we say, what we believe or what we want to prove. Okay, what we want to prove, we will put it into the alternative hypothesis. So the hypothesis in the exercise is that the average weight mu is less than 20 grams. So that's why our alternative hypothesis will be mu less than 20. Okay? And the new hypothesis and the non-hypothesis will be mu equal to 20, or it can be mu equal or less than 20. Is also okay. Okay? So that is the hypothesis. The first step, you have to calculate the hypothesis. What is the next one? What is the next step? When you have developed the hypothesis, what is the next step in hypothesis testing?
We calculate the test statistic.
Yeah, we will calculate the test statistic. All right. So in this case, suppose that we do not know, okay, let's assume that we do not know the value of sigma square, and we have to use the sample variance to estimate it. And when we take the random sample of 36 tea bags, we get the sample variance, okay, S square equal to 1 gram square, okay. And then what will be the test statistic that we need to calculate? Do we have to calculate a z value, or do we have to calculate a t value? In this case,
T value.
yeah, we have to calculate a t value because we do not know the exact value of sigma square. All right. So how can we calculate the t value here? The formula that, as we know, the x bar minus what? V, okay, and divided by s. But in this case, when you the null hypothesis, we will assume that the null hypothesis is true until you can prove that the null hypothesis is rejected. Okay, so here we assume that the null hypothesis is true, which means that mu is equal to 20. Okay, and t is equal to x bar, in this case the observed value of x bar 19.7 minus, okay, the suspect value of mu in HO, okay, the stated value of mu in HO, that is, okay, and divided by s, which is 1, sorry, s divided by the square root of n, okay, and this one is square root of 36. And what is the value? What is it?
Minus 1.8.
1.8. Okay, thank you. All right, minus 1.8. All right, so what is the next step?
We will calculate the p-value.
Okay, calculate the p-value. How can you calculate the p-value of t?
We will calculate the degree of freedom.
Okay. So the degree of freedom, we have n, the degree of freedom, okay, n minus 1, which is 35, right? Okay, and now we will determine the level of significance. So the level of significance, for example, we take the level of significance of 5%, like the previous case. Okay, so what will be the critical value? Can you look for the value in the table? Now, look up the value in the table. What is it?
One 1.6896.
Oh, okay. T the T of alpha. Okay, so in this case, we will use T alpha or T alpha divided by 2.
T and phi.
Yeah, all right. Because this one is a one-sided test, okay? One-tailed test. Then we will have to use T alpha, okay? Which is T 0.05 and the degree of freedom of 35, okay? Look up in the table, we get the value of 1 point what? I forgot. What is it?
1.6896.
6896. Okay. All right.
96.
Okay.
689.
68689. 6. All right. Okay, so it is approximately to 1.69. All right. Okay, so here, what is the next the next step is to determine the rejection zone. Okay, the rejection zone. What is it? Here is a what is left-sided. This one is a left-sided test. What is the rejection zone for this test? The area where we reject the null hypothesis.
T smaller than minus T alpha over 9 minus minus 1. T will smaller than the T smaller than 1.69.
Okay, good. All right, so the rejection zone will be from negative infinity, okay, to minus, right, minus 1.6896. All right, okay, so as long as the observed value of t, or the statistic here, the test statistic here, fall into the rejection zone, then we can reject the null hypothesis. So obviously, in this case, this test statistic or the observed value of t is minus 1.8, okay? And this fall into the rejection zones, and that's why we will reject, okay? That's why we can reject, okay, HO, all right? And then support, okay, we find enough evidence to reject the null hypothesis HO, and we can support the belief that the average weight of all tea bag manufactured by this company is less than 20 grams at 5% level of significant. All right, so draw the conclusion. Okay, so draw the conclusion here. Okay, at 5% level of significant, okay, the average weight of all tea bag manufactured by this company is less than 20 grams. Okay, that is a hypothesis testing. We find the evidence to support the hypothesis. All right. Okay, so in hypothesis testing, okay, we have the first step is to state the hypothesis. Okay, then we calculate the observed value of t. We calculate the test statistic. In this case, we use a t-test. Then we calculate the observed value of t. In other tests, when we have to use different distribution. For example, you will have to calculate an observed value of f or observed value of chi-square or so on. All right, depends on which test you are conducting. All right, so please consider that. In this case, we are using a t-test. Then we will calculate the t observed value of t. Okay, and we determine the rejection zone like we just have done. All right, and to see whether the test statistic is in that rejection zone. Okay, and then we draw the conclusions. Okay. Okay, so those are steps. These are the steps that we have to conduct when we want to do a test, a hypothesis testing. All right, we have almost 4 steps in doing the test. And here's the formula to calculate the test statistic for a t-test. We take the observed value of the estimate, okay, the observed value of estimate minus the suspect value and divided by the standard error of the estimate. Okay, that we get the then we will get the test statistic for a t-test. Oh, that's the end of the slide. Okay, so we have done with the review of statistic and probability. Okay, so please remember that you have to have this we have to have this basic statistic and probability in hand so that it will be easier for us to learn econometrics. All right, I have a small quiz for you. Where is that? Let me try to find out. In the channel introduction, here, right before the meeting, you can see that we have the tab here. Okay, so we have a tab. We have a pause right before our meeting here. You can click there, but it is not open yet. I will open the link and then you click there to do the quiz. Okay, we have a quiz here. Wait for a minute. Okay, so the form is opened. You can click on the link. Okay, you can click on the link and do the quiz. Can you access? Can you access to the test to the quiz?
Yes.
Okay. Okay, thank you. So do it.
I couldn't access the test.
You can refresh your browsers, or you close the tab and open it again.
Yes, I have it. Thanks.
Okay, thank you.
Cô ơi, em, reset browser tải lại browser rồi nhưng mà vẫn không thấy bài tập cô ạ.
À, được chưa?
Em chưa thấy lắm.
Tắt thử đi rồi mở lại giúp cô. I have got 7 response. We have 38 response. Forty-five. Have you all finished?
No.
Okay. Finished? Okay, so I will close the quiz now. Receive 89 responses. Now close it. And we will check the answers. All right. So our questions is, if we have we care about the weight of watermelon harvested by a farm. Okay, and we take a 15 random watermelons, and the average weight is 3.62 kilograms. Okay, the sample variance is 0.01. What is the 95 confidence interval for the mean weight? All right. So here we have what is it? We have okay. So we have x bar here equal to 0.62, right? We have s equals 0.01. All right. What else? We have n, okay, 15. What else? And alpha is
sample variance is 0.01, so it's s squared.
oh yeah. So okay, 0.1, right? Sorry. 0.1. This one is 0.05. Okay, now we have to construct the confidence interval, 95% confidence interval for the mean weight. All right, so it will be the x bar minus. In this case, we have to use critical z or critical t. Z or yeah.
T.
But know the exact value of the population. Yep, the population variance. Then we have to use t. Okay, t of 0.025, and the degree of freedom is what is the degree of freedom?
14.
40, right? And multiply by s divided by the square root of n. Okay, to x bar minus t critical t, and multiply by s divided by square root of n. Now just plug in the number. We have x here, 3.62 t. What is the value of t? What is the value of critical t?
2.1448.
Bao nhiêu ạ?
2.1448.
1448. Okay. S1 and n is 15. Just plug in the number to get this value. Các bạn có tính ra được
Yes,
cái
yes, approximately 3.5646.
Okay. Cái này hả?
Vâng.
Okay.
Thực ra nó chỉ là 3,5646 thì xấp xỉ 3,3565.
Okay. So I can cô lấy cái approximately thôi. Đúng không ạ? Okay. So this one is the correct answer. All right. So check your answer. What do you get here? All right. We have we have 71 out of 89 people provide the right answer in this case, so which account for 80% of our class. It is a high number. Good. But some of you do a lot of you make a mistake here. Why do you get this number? I know.
Okay. The variance, square root.
The variance is not square rooted, right? Okay, right. And this one is very simple one. Okay, so most of you choose the correct answers. That's good. All right. So some who do the who choose the wrong one, you can do it again and realize your mistake. And next time you see the same questions, do not make the same mistake. Okay. All right. About the homework. About the homework, I see that some of you have not submit the assigned homework. Oops, what happened? What happened to this? Okay, some of you have not submit the assigned homework. Remember that this will count toward your what is it? Your attendance score. Okay, some of you have not submitted it. Some of you have viewed it, but do not submit it, the answer. Remember that. Example. Remember when you when you attach the file, remember to click on the submit. Click on the submit button. Okay. If not, it will not. The status will be like viewed or not submitted or something like this. All right. Thank you. So our class today will end here. All right. Next time we have done with the review of statistics and probability. Next time we will begin with the things of econometrics. All right, and start with the regression analysis and the simple regression model. All right. Do you have any questions for today's class?
Yes.
Yes. What is it? What is the questions?
Cô ơi, cô xem lại cái bảng những người chưa nộp bài được không ạ? Tại vì hôm qua em có nộp bài rồi nhưng mà em vừa thấy tên em ở trong danh sách.
Ok. Nếu mà bạn submit rồi, bạn turn in rồi thì nó ấy thôi. Nó sẽ ở đây. Đợi có một chút. Nè, có một số bạn chưa nộp bài. Nè. Các bạn đã xem này cũng là chưa nộp bài này. Cô sẽ check những cái bạn đã xem. Vì có một số bạn các bạn bị nhầm. Các bạn attach file vào nhưng mà các bạn không submit. Nó sẽ chỉ hiện là đã xem thôi. Còn nếu như các ơi,
cô kiểm tra giúp em Phạm Thị Phương được không ạ?
nếu như các bạn không có tên ở đây thì là đã nộp bài rồi.
Cô ơi, em có gửi lại vào email cho cô hôm qua rồi ạ.
Ok.
Em là Vũ Linh Chi ạ.
Cái đấy nhá, ví dụ sau này khi mà cô làm điểm ấy, nếu như các bạn thấy một điểm của mình không có, các bạn bị trừ cái điểm ở cái hôm đó, thì các bạn có thể là các bạn viết mail lại cho cô và bảo là em hôm đấy em có cái vấn đề gì đó và em gửi gửi qua email chẳng hạn, đúng không ạ, ví dụ như vậy, và kèm theo cái minh chứng, thì lúc đấy cô sẽ check lại và cô sẽ chỉnh sửa cái điểm cho các bạn, đúng không ạ. Nhiều khi cô làm là cô đến cái lúc cô làm điểm cô sẽ không thể nhớ được những cái việc là các bạn gửi ngoài hay là như thế nào đâu, được chưa ạ? Đó, thì cô sẽ chỉ cô dựa vào cái kết quả ở trên team này thôi để cô làm điểm nhá, các bạn lưu ý những cái điều đó, được chưa?
Em thưa cô, bài tập là sẽ tính vào điểm chuyên cần đúng
Ừ, đúng rồi, bài tập
không ạ?
tính vào điểm chuyên cần, đúng rồi ạ. Any other questions?
So about the hypothesis testing and calculating the data. In reality, usually the sample size is really large. In certain experiments, the sample size is really large. So my first question is, how big is the sample that we take is enough so that we can, so that the results can be reliable? That's my first question. Secondly, we do not always have enough, like the enough true data to calculate exactly what we want. So, is there any alternatives or any solutions to this problem?
For the first questions, how big is the sample size that is enough for statistical inference? So for statistical inference, the sample size is as big as possible. The bigger the sample size, the better the estimation, or the better the statistic inference is. All right, but how big is enough? The sample size should be bigger than at least bigger than 120. That is the minimum of the mean that that is best, that is good for statistical inference. Okay, and but remember that the bigger the sample size, the better the statistical inference. And for the second one, we do not have the data for the whole population. Okay, that is real. Okay, in reality, we usually do not have enough data for the whole population of interest. And the way that we do here is just we collect a random sample, like we say, and we calculate the statistic, the sample statistic, and just get approximations of the population parameters. We cannot get the exact value of the population parameters. Okay? Cái việc mà chúng ta chỉ có được cái số liệu mẫu thì chúng ta không thể nào mà tính được chính xác cái thằng tổng thể của chúng ta được. Và bởi vì vậy cho nên là chúng ta chỉ ước lượng thôi, chứ chúng ta không bao giờ tính một cách chính xác các cái tham số của tổng thể cả, đúng không ạ? Chúng ta chỉ có thể có các cái ước lượng, ví dụ như là ước lượng điểm là nó có thể bằng bao nhiêu, hay là ước lượng khoảng như vừa rồi chúng ta nói là nó có thể nằm trong cái khoảng nào, chứ không bao giờ chúng ta không thể có được cái exact cái exact number được, đúng không ạ? Khi mà kích thước mẫu nó càng lớn thì các cái khoảng của các bạn nó càng ngắn, thì chúng ta sẽ biết nhiều hơn về cái chúng ta sẽ đến gần hơn với cái population parameters thôi, đúng không ạ? Hoặc là cái point estimation của các bạn nó sẽ closer, nó sẽ gần với cái true value của cái population parameters thôi, chứ chúng ta không thể tính được chính xác cái value của cái parameter, của cái population parameters, đúng không ạ?
Ý của em là tức là nhiều khi trong thực tế thì cái thông tin nó không hoàn hảo ấy. Tức là các mô hình kinh tế thì thường họ assume là con người rất là lý tính và luôn luôn đưa ra lựa chọn đúng là một. Cái thứ hai là họ luôn luôn có thông tin hoàn hảo. Thì trong thực tế thì theo như em quan sát thấy thì thứ nhất là con người không phải là không hoàn toàn lý tính là một, hai là cái thông tin nó không hoàn hảo một tí nào cả. Thế thì tức là nếu như mà đưa vào các cái bài toán xác suất thống kê thì em thấy là có những cái ví dụ như là mình phải khảo sát, mình muốn lấy số liệu của tất cả các ngân hàng trên Việt Nam chẳng hạn, nhưng mà chỉ có 4 đến 5 ngân hàng lớn nhất là họ công khai thông tin thôi, thì liệu những cái ngân hàng lớn nhất hoặc là uy tín nhất đấy nó có đủ cái số liệu, nó có đủ valid để thay thế cho gần 20 các ngân hàng còn lại không? Làm
Đúng rồi, cái đó thì mình phải xem xét cái độ cái representation, cái mức độ đại diện representative của cái sample mà các em lựa chọn, đúng không ạ? Ví dụ như là khi mà cái sample đấy nó có những cái đặc tính, nó có những cái đặc điểm mà nó giống với cái tổng thể của chúng ta, nó đại diện cho tổng thể của chúng ta, thì lúc đấy cái statistical inference của chúng ta nó mới là reliable, đúng không ạ? Còn trong trường hợp mà khi mà tôi nghiên cứu về hệ thống các cái ngân hàng thương mại ở Việt Nam, thế nhưng mà cái sample của tôi ở đây tôi lại chỉ lấy 4-5 cái ngân hàng lớn, thì khi đó là cái số liệu đấy của em nó sẽ không đủ để mà chúng ta, không đủ đại diện để mà chúng ta có thể đưa ra được các cái inference nó tốt về cái hệ thống ngân hàng của chúng ta được chưa ạ? Vì vậy cho nên là khi mà lựa chọn mẫu ấy, thì chúng ta cần phải lựa chọn một cái mẫu mà nó có cái tính đại diện cao cho cái tổng thể của chúng ta, được chưa ạ? Còn trong trường hợp như vậy, trong những cái trường hợp mà em nói như vậy thì chắc chắn là mình sẽ phải phải lựa chọn một cái tổng thể khác rồi, chẳng hạn như là tôi quan tâm đến tôi chỉ quan tâm đến những cái ngân hàng lớn thôi chẳng hạn, ví dụ là như vậy, đúng không ạ? Chứ không phải là tất cả cái hệ thống ngân hàng thương mại ở Việt Nam đó, thì các bạn lưu ý. Còn trong trường hợp mà tôi quan tâm đến hệ thống thương mại, ngân hàng thương mại ở Việt Nam, thì để cái mẫu của mình mà nó đại diện cho tổng thể thì tôi phải tìm cách tôi lấy được cái data của các cái thằng ngân hàng bé nữa, đúng không ạ? Các cái ngân hàng nhỏ hơn ở mỗi size thì mỗi size thì chúng ta nên lấy một hoặc là một vài các cái ngân hàng đại diện cho các cái nhóm đó, đúng không ạ? Nếu như mà các bạn có học đến nghiên cứu các cái phương pháp nghiên cứu khoa học ấy, thì các bạn sẽ thấy là chúng ta có các cái cách thức chọn mẫu để mẫu cho nó tiêu biểu, cho đại diện cho tổng thể, đúng không ạ? Chẳng hạn như là chúng ta sẽ có các cái mẫu, chúng ta có cách chọn mẫu như là chọn mẫu phân tầng, đúng không ạ? Chọn mẫu phân tầng thì chúng ta sẽ chia cái tổng thể của chúng ta thành các cái tầng khác nhau, đúng không ạ? Các cái tầng với các cái đặc điểm khác nhau, và mỗi tầng đấy thì chúng ta sẽ lấy ra, chúng ta sẽ random chọn một số các cái quan sát từ các cái tầng đó, đúng không ạ? Và cuối cùng chúng ta sẽ form nó lại thành một cái random sample của chúng ta, thì đảm bảo là cái sample đấy nó sẽ có những cái đối tượng mà nó đại diện được cho các cái đối tượng ở trong tổng thể, đúng không ạ? Thì cái việc mà chọn cái sample nó có cái tính đại diện, đúng không ạ? Có cái tính đại diện cũng là một cái một cái yếu tố quan trọng, đúng không ạ? Cũng là một cái yếu tố quan trọng cho cái việc mà chúng ta có thể cái statistical inference của chúng ta nó valid, đúng không ạ? Còn cái việc mà chúng ta nói là có những cái giả định của chúng ta mà nó không hold in reality ấy, đúng không ạ? Thì chính vì thế, chính bởi vì là những cái giả định đó nó không hold in reality, thì chúng ta mới có các cái biến của chúng ta nó là random sample, nó random variables như vậy, đúng không ạ? Nếu như là tất cả các cái giả định của chúng ta nó đều được nó đều được hold trong thực tế của chúng ta ấy, thì lúc đó các cái ước lượng của chúng ta lúc này nó sẽ có cái kết quả, nó sẽ là các cái giá trị chính xác. Ví dụ như là nếu như mà tôi giả định là other thing constant chẳng hạn, đúng không ạ? Thì một cái mức, đúng không ạ? Một cái mức other thing constant thì một cái mức giá này, đúng không ạ? Nó sẽ chỉ tương ứng với một cái lượng cầu mà thôi, Thế nhưng mà trong thực tế, đúng không ạ? Trong thực tế là không phải là other thing constant mà các thứ nó sẽ đều thay đổi, nó cũng đều có tác động. Mỗi trường hợp nó có một cái đặc điểm khác nhau. Chính vì vậy mà với một cái mức giá, một cái price level thì chúng ta sẽ có rất nhiều các cái demanded quantity khác nhau ở các cái thời điểm khác nhau hay là các cái thị trường khác nhau. Đúng không ạ? Thì đấy nó chính là thể hiện cho cái statistical relationship giữa các cái economic variables của chúng ta. Đúng không ạ? Và các bạn lưu ý là đó mới là cái lý do, đúng không ạ? Đó cũng chính là cái lý do tại sao mà chúng ta chỉ cố gắng là đi estimate nó thôi, đúng không ạ? Chứ không cố gắng là calculate cái exact value của các cái biến. Đúng không ạ? Cô trả lời có đúng ý không?
Dạ, có một phần là em hiểu rồi, nhưng mà vấn đề là các cái vấn đề như là con người thì họ không hoàn toàn lý tính này, rồi thông tin không hoàn hảo, rồi các cái trường hợp mà bội ước ở trong thị trường thì cũng rất là phổ biến, mà thường thì nó gây đến sai số rất là lớn. Thì không biết là có cách nào để nullify cái này không?
Có cách nào để mà chúng ta giải quyết những cái vấn đề này không thì như chúng ta vừa mới nói ạ, đúng không ạ? Bởi vì là không giải quyết được những cái vấn đề đấy, hoặc là có giải quyết được ấy thì cũng chỉ giải quyết được, chúng ta sẽ không bao giờ mà chúng ta có được cái exact value cả, đúng không ạ? Mà luôn luôn là những cái approximation mà thôi. Được chưa? Chẳng hạn như là những cái hành vi của con người, đúng không ạ? Những cái hành vi của con người thì nó rất khó để mà chúng ta lượng hóa, mà chúng ta đưa nó vào trong mô hình được, đúng không ạ? Vì vậy cho nên là nó sẽ luôn luôn là những cái biến ngẫu nhiên, mà nó sẽ có tác động là các cái yếu tố ngẫu nhiên mà có tác động đến cái biến của chúng ta. Và đương nhiên là khi đó là gì ạ? Cái kết quả mà chúng ta thu được ấy, đúng không ạ? Thì nó sẽ chỉ là tương đối thôi, chứ nó không nó sẽ chỉ là tương đối, nó mang tính số đông, chứ nó sẽ không đúng cho tất cả các quan sát ở trong cái tổng thể của chúng ta đâu ạ. Đúng không ạ? Mà cái kết quả mà chúng ta thu được ấy, nó sẽ chỉ là cái kết quả mà phần lớn, đúng không ạ? Là cái kết quả mà đại diện cho phần lớn cái tổng thể của chúng ta thôi. Như các bạn thấy là ở trong thực tế của chúng ta cũng vậy. Đúng không ạ? Ví dụ như là hầu hết là chúng ta học nhiều, đúng không ạ? Thì chúng ta sẽ được điểm cao, đúng không ạ? Chúng ta tập trung chúng ta sẽ được điểm cao, nhưng vẫn sẽ có một số trường hợp do những cái điều kiện nào đó mà mặc dù chúng ta đã học rất nhiều, đúng không ạ? Chúng ta đã học rất nhiều, chúng ta rất chăm chú rồi, nhưng mà điểm của chúng ta nó vẫn không cao, đúng không ạ? Thì đấy nó không phải là trường hợp số đông mà nó chỉ là trường hợp số ít thôi. Các cái kết quả mà chúng ta thu được ở đây nó là các cái kết quả mà nó đại diện, đúng không ạ? Nó đại diện cho số đông ở trong tổng thể, chứ nó không phản ánh tất cả các cái trường hợp có thể xảy ra ở trong tổng thể. Thấy chưa? Những cái mà như chúng ta nói là con người thì không lý tính, rồi thì cái gì nữa nhỉ? Thì không đầy đủ chẳng hạn, đúng không ạ? Ví dụ như vậy, đúng không ạ? Chính những cái điều đó nó sẽ tạo nên cái yếu tố ngẫu nhiên ở trong biến của chúng ta, đúng không ạ? Và vì vậy cho nên là chúng ta không bao giờ chúng ta cố gắng đi ước lượng cái yếu tố ngẫu nhiên đó cả, đúng không ạ? Chúng ta chỉ ước lượng những cái phần nào mà chúng ta có thể ước lượng thôi, và chúng ta cố gắng tối thiểu hóa cái phần random, đúng không ạ? Chúng ta tối thiểu hóa cái phần ngẫu nhiên đó mà thôi. Cố gắng xác định những cái phần mà chúng ta có thể xác định được và tối thiểu hóa những cái phần mà ngẫu nhiên, đúng không ạ? Để mà chúng ta có được cái best estimation của cái biến mà chúng ta quan tâm, của cái mối quan hệ mà chúng ta quan tâm. Ok.
Dạ vâng, cảm ơn cô.
Ok. Any other questions?
Cô ơi, em có gửi tin nhắn cho cô ở trong team ấy ạ, thì lát nữa kết thúc buổi học cô có thể check tin nhắn của em được không ạ?
Ok.
Em cảm ơn ạ.
Rồi, nếu như các bạn không còn, if we do not have any other questions, we can end the lecture here today. Okay. So see you on Fridays. Okay. Goodbye.
Goodbye, teacher.
Okay.
Goodbye, teacher.
Bye bye.
Goodbye, teacher.
Thank you. Bye.
Em chào cô.
Bye.